Hi, my name is Daniel Varon. I'm a research associate in the Atmospheric Chemistry Modeling Group here at Harvard, and I'm delighted today to be able to present some of our work at Harvard Climate Action Week. And in particular, I'll be talking about a software tool we've been developing in our lab for the last few years called the Integrated Methane Inversion, or IMI. And it is a user-friendly cloud computing tool for monitoring methane emissions with satellites. In my presentation, I will cover the methane problem, why we need tools like the IMI, how the IMI works, and some of the problems that we can apply it to support efforts in methane emission mitigation. So atmospheric methane has become a major focus of both science and policy. On the science side, there's been a long-standing debate over what is driving recent methane trends. As you can see from this figure on the left, over the last 40 years, methane concentrations in the atmosphere have been increasing rapidly in fits and starts. The growth was relatively uniform into the early 1990s, but then started to taper off and actually stagnated in the early 2000s. Around 2007, methane concentrations started to grow again and have been accelerating ever since. And there are multiple factors that could explain this variability. It could be due to changes in methane emissions, such as from wetlands or oil and gas, or it could be due to changes in methane's primary sink in the atmosphere, which is the hydroxyl radical, OH. It's a very reactive species that eats up methane and a variety of other trace gases in the atmosphere. And so this is still heavily debated. At the same time, on the policy side, methane has been identified as the lever to slow near-term climate change. And that's because it is a strong greenhouse gas responsible for about 30% of the climate warming that we've experienced to date. But unlike CO2, it has a relatively short atmospheric lifetime of just 10 years. So that if we are to cut methane emissions today, we'll see benefits almost immediately. Now, it needs to be said that cutting methane is not a substitute for cutting CO2, because by the same logic, over a 100-year timeline, it's the longer-lived greenhouse gas CO2 that really matters. But if we're going to achieve our climate goals in the near term, keeping a global mean temperature rise below 1.5 or 2 degrees Celsius, for example, we need to go after methane emissions immediately. And this has become increasingly urgent in the last couple of years when we've seen an uptick, a continued acceleration in the methane growth rate for reasons that are not well understood. And so for all of these reasons, there has been a strong need for better understanding of methane emissions. But this is a really difficult problem because methane comes from a wide range of different sources, both natural and anthropogenic. Natural emissions are largely from wetlands. Wetlands account for about a third of the global methane emission budget, but there are smaller natural emissions from geological seeps, termites, and fires. Anthropogenic or human-made methane emissions are more of a mixed bag. There are important contributions from many different sectors, including livestock, oil and gas, coal mining, wastewater, landfills, rice cultivation, and so on. Now, in principle, decreasing anthropogenic methane emissions should be easy because simple measures can go a long way. In oil and gas, we can fix leaks, we can change venting practices, we can flare excess gas or better use it, send it to market. In the waste sector, methane gas produced in landfills can be recovered and used as fuel. We can use digesters to digest gas from manure ponds and wastewater plants. We can change cattle feed to reduce methane emissions from livestock. We can even adjust rice cultivation practices to decrease methane emissions. But a major problem is that the vast majority of these anthropogenic methane emissions come from millions of point sources that are scattered all around the world. Things like the ventilation shafts of underground coal mines, or the feedlots where the cattle live, landfills that are found in cities around the world, and the millions of oil and gas facilities around the world, like these production well pads shown here in Utah. And these point sources are very complex. They have highly variable emissions. They tend to be highly intermittent. And this translates to large uncertainties in national methane emission inventories. national inventories are the official methane emission estimates of individual countries, and they're usually produced using bottom-up methods that estimate emissions from the product of activity rates, like the number of cows in the country, and emission factors, or the typical emission per cow. In contrast, top-down methods can be used to estimate methane emissions using observations of atmospheric concentrations taken either at the ground or from aircraft or as we'll see, from satellites. And these different estimates often don't match up well. This plot, shown here on the left, is from a paper by Tia Scarpelli et al. In 2022, and it compares a range of different methane emission estimates for some of the top emitting countries around the world. The gray and black points are bottom-up methane emission estimates, for example, from the International Energy Agency, IEA, in 2019, in these gray X marks. And the green and yellow markers are for top-down satellite-based methane emission estimates. Now, the x-axis of this figure is logarithmic, and it's showing the methane emission totals in teragrams per year. And you'll see that for many of these countries, there are order of magnitude differences between the estimates, even within the bottom-up values. Now, this is a major problem for climate policy because these large uncertainties lead to a lack of confidence in climate action. The individual countries report these annual emission inventories to the UN Framework Convention on Climate Change, or the UNFCCC, and they're the basis of the global stocktake, which is a measure of how well the world is doing on climate goals, and also for the nationally determined contributions, or NDCs, that countries set to decrease their emissions. So if we have such large errors in these bottom-up emission inventories, that translates to large errors in our starting point for climate policy, in our ending point, and for the progress along the way. And so this really undermines climate action. Now, something we can do to improve the situation is we can bring top-down information from atmospheric observations to bear on the inventories to evaluate them and hopefully improve them. And the process of doing this is referred to as an inversion. The way it works is we start with a prior estimate of methane emissions, naturally from a national inventory. The example here is for a smaller region of interest than a country. It's for the Permian Basin in Texas and New Mexico. It's the largest oil and gas producing basin in the United States and among the largest in the world. So the prior estimate of emissions is our best guess. It's a starting point. We then apply an atmospheric transport model, which simulates flow through the atmosphere, to predict what concentrations of methane we would observe in the atmosphere, whether from an aircraft or from the ground or from a satellite, if those were the true emissions. We then compare the predicted concentrations with the actual observed concentrations, and the inversion consists in that comparison, in adjusting the map of methane emissions up or down in different areas to produce a better match between the simulation and the observations. And the end result is what we refer to as a posterior or optimal emission estimate. Now, there's been a lot of interest in doing this type of work with satellites because satellites have routine global coverage. And this is the current and planned satellite observing system for methane. So I'll review some of the capabilities we have. You'll see that there are very many instruments here. The ones underlined in green are launched and active. They fall into two broad categories: area flux mappers, which are designed for global and regional scale analysis, and point source imagers that can zoom into very high resolution to resolve individual plumes from industrial facilities. So first, how do these instruments work? So these instruments see methane in the atmosphere from backscattered sunlight in the shortwave infrared part of the light spectrum. Methane has a unique absorption signature in the shortwave infrared, and so the instruments look at light that travels through the atmosphere from the sun and then reflects from the Earth's surface back up through the atmosphere to the satellite, and they look for that signature of absorption in the shortwave infrared to infer the amount of methane that was in that slanted column of the atmosphere. We can compare all of these different instruments in terms of the magnitude and spatial scale of emissions they can quantify. The oldest instrument that we've had since 2009 is GOSAT. So GOSAT is providing the longest historical record of global methane concentration data from space. It's a very high quality instrument, very precise measurements, but the spatial resolution is relatively coarse. So it mainly provides information on emissions at continental scales. In 2017, we got a game changer in TROPOMI, which, like GOSAT, has global coverage, but it observes the whole world every day, and does this at much finer spatial resolution of just a few kilometers. And so this gets us down to the regional scale, for example, of individual oil and gas basins like the Permian. Here I'm showing 1 month of TROPOMI observations for the Permian, where we can see clear hotspots of methane concentrations over the Delaware subbasin, which is to the west, and the Midland subbasin here to the east. These are the two centers of methane or natural gas production in the basin. Now, what TROPOMI can't do is resolve the individual point sources that are giving rise to these large regional hotspots. And that has really been the focus of the point source imagers, starting with the target mode instruments like GHGSat. So these satellites don't have global coverage in the sense of TROPOMI and GOSAT. They can observe anywhere in the world, but they have to be tasked and targeted to zoom into an area of interest. They observe that area, usually a relatively small patch of the Earth's surface, but they do it at a really high spatial resolution, down to about 30 meters. And this allows them to resolve methane emission plumes coming from individual industrial facilities like oil and gas facilities in the Permian or landfills in India. And this has been a really exciting development in satellite remote sensing of methane, because it allows us to directly identify opportunities to reduce emissions and generate actionable information for emission mitigation. There's been so much interest in the point source capability that it's actually led to the expansion of our methane observing system to include satellites not originally designed for methane sensing, including land surface mappers like Sentinel-2 and Landsat. These are instruments that produce data we're used to seeing, for example, on Google Earth, that show high-resolution visible surface imagery, but they also have shortwave infrared bands, and we can use them, it turns out, to image very large methane plumes around the world at high resolution. And that capability was even more recently extended to geostationary orbit, starting with the U.S. Geostationary Operational Environmental Satellites, or GOES. This is the United States Operational Weather Satellite System. And what makes it unique on this chart is its position in geostationary orbit. So what do I mean by that? All of the other instruments are in low Earth orbit, which means that they orbit a few hundred kilometers overhead. They complete several orbits per day, and they usually pass overhead at around the same local time every day or every few days. GOES is much further away, more than 30,000 kilometers away. In geostationary orbit, it revolves around the Earth at the same rate as the Earth rotates, and so it's always staring at the same area of the surface. So GOES in particular takes snapshots of the Western Hemisphere every 5 to 10 minutes, and with its shortwave infrared bands, we can use this to essentially film very large methane point releases from geostationary orbit. This is an example of a large release from a natural gas pipeline in Mexico called the El Encino La Laguna, or EEL pipeline, that transports Permian gas to Mexican markets. On May 12, 2019, GOES picks up this 3-hour release of about 1,200 tons of methane from the pipeline, and this was a maintenance event. It came from what's called a block valve station. It's a facility that pipeline operators use to segment the pipeline, to empty a segment of the pipeline before conducting maintenance. We can see similar events in the United States as well. Here's an example of a double pipeline release seen by GOES from a pipeline in Indiana. This one, which occurred June 15th, 2020, was observed also by TROPOMI several hours later over Illinois. And with GOES from geostationary orbit, we can actually trace those plumes back to their origin one state over. So we have a really wide range of capabilities for observing methane from space. And as exciting as those point source imagers are for their direct climate actionability, those large point sources account for a relatively small fraction of total methane emissions, for example, at the national or continental scale, that are so critical for climate policy. And it's the area flex mappers like TROPOMI and GOSAT which can give a clearer picture of those global and continental and national scale emissions. So this would be the focus of my talk today, will be this capability for global mapping with TROPOMI. The video on the bottom left here is showing the TROPOMI observing configuration and how it covers the whole globe every day, producing more than 100 million observations per year. The image in the background is showing a global map of methane concentrations from TROPOMI for the year 2021. And we can see in this map these large hotspots that are emerging from areas with high emissions. For example, in China, in India, from the Sud wetlands in South Sudan, from across Nigeria, and from the Permian Basin in Texas and New Mexico, to name a few examples. And one of the things that we can do with this very large data set is we can quantify emissions coming from these hotspots, these regions of interest, and also from individual countries. So this plot is showing satellite-based estimates of total methane emissions coming from the top 10 emitting countries. The bulk of the emissions come from the top 5, China, India, the US, Brazil, and Russia, but with very different sectoral mixes. Emissions from China are largely from coal mining and livestock. Emissions from the US and Russia have important contributions from oil and gas, and in India and Brazil, the main sources of methane are livestock. So all of these countries have different priorities and levers that they can use to cut their methane emissions. Critically, of these top 10 emitting countries, only 5 have signed the Global Methane Pledge of 2021, now signed by more than 150 countries, to collectively cut methane emissions by 30% by 2030 relative to 2020 levels. So there's still a lot of work to do to get more high-emitting countries on board to coordinate methane emission reductions. And this kind of information that's so critical for global climate policy can be generated from the inversion procedure that I outlined earlier. And so the question now is, how do we get this into the hands of stakeholders, the policymakers and industry leaders who are actually driving the methane emission mitigation efforts? And this is where the IMI, the Integrated Methane Inversion, comes in. The IMI is a tool for stakeholders to quantify total methane emissions from satellite data. IMI users can quantify methane emissions for any region at 25-kilometer resolution with careful accounting of uncertainties, compare their results to bottom-up emission inventories, set up near real-time continuous monitoring for their region of interest, and run the IMI and access it freely on the AWS cloud, and as I'll show shortly, also through a more user-friendly dashboard. Under the IMI hood are advanced inverse methods that have been extensively documented in the scientific literature and through the IMI, made easy to use. A team of Harvard developers continuously working to improve the capabilities of the tool, and an open source code base for total transparency of methods and results. Now, the IMI is really designed to be applied to the problems of non-expert stakeholders, whether they're from national, state, or local governments around the world, international organizations, industry groups, NGOs, or advocacy groups. Users can select a region and period of interest using a simple configuration file, and then run an inversion of satellite observations on the cloud. The algorithms running behind the scenes are developed and maintained by our group at Harvard, and of course the goal is to produce actionable total emissions data for regions of interest. I want to emphasize that this tool is completely open source and open access. It's freely available on the AWS marketplace, and that is to ensure transparency, reproducibility, and credibility, which are totally essential for applications to climate policy. Now, this is an example of how IMI version 1.2, the latest version available on AWS, can be applied to estimate methane emissions from a region of interest. Here, the Permian Basin, again in Texas and New Mexico, and it's applied to a 1-month period, May 2018. So we're trying to estimate the average methane emissions that came out of the basin during that month. The user starts by selecting their region and period of interest. Here it's the Permian Basin at 25-kilometer resolution for a month. But this can be as simple as the latitude and longitude bounds of a rectangular domain and a start and an end date. There's then what we call an IMI preview feature. And this is a feature that we introduced to allow users to get a sense of what to expect from their inversion before they commit to actually running it on the cloud. Running the inversion on the cloud uses AWS compute resources and their associated fees. So we want users to be able to configure their inversion and feel confident that it's going to return useful results before committing to running it on the cloud. The preview allows the user to check data quality and to view the prior emission estimates that are going to be used in the inversion, to view the satellite observations that will be used in the inversion that are available on the cloud. Here are 20,000 observations for the Permian Basin for May 2018, seen by TROPOMI, and then also to estimate the expected dollar cost. Once the user is happy with their configuration, they can submit the inversion with a single command, and it will run behind the scenes and deliver a posterior emission estimate. So in the example here, we started with a prior estimate from the Environmental Defense Fund for the Permian Basin, which puts total methane emissions from the basin at 2.7 teragrams per year. We then confronted that prior estimate with 20,000 TROPOMI observations during May 2018 and inferred a posterior optimized methane emission 30% higher at about 3.5 teragrams per year. We've had a lot of interest in this tool so far. We currently have 50 to 100 users across more than 10 countries and about 20 interested organizations who are running the IMI, including the 4 that I've highlighted here. So that was IMI version 1.2, but later this month we'll be releasing IMI 2.0, which will greatly expand the capabilities of the tool. We are expanding input options, including options to incorporate information on point sources observed in the region of interest. We are introducing a suite of multi-scale inversion capabilities from the global scale down to the scale of small regions of interest, like individual oil and gas basins, but even individual urban areas. And we're enriching the output to include, for example, information useful for continuous emission monitoring, where we update emission estimates as satellite data roll in, and also options for national and sectoral disaggregation of results. We also have a host of future developments in the works. We're working on improving the user dashboard to make the tool more user-friendly and to improve the ease of input and output management. We want to exploit new satellite data sets as they become available, starting with MethaneSat, which launched just a few months ago in March, and will be delivering very high-quality methane data for global oil and gas basins, and also the up-and-coming Carbon Mapper mission for point sources. We're working on improving the resolution of the IMI from 25 kilometers down to 12 kilometers, and I'll show an example of that new feature in action. And then also we have started working on extending our capability for methane to other greenhouse gases, and especially CO2. This is working towards an integrated carbon inversion, or ICI. Okay, in parallel with all of that development, we are also working on an operational platform for accessing the IMI. And this is a web-based user interface that we're calling Integral Earth. There's a mock-up shown here of what a customized emission dashboard for the Permian Basin might look like through this tool. And the goal is to use this to really put the power of satellite observations more easily into the hands of the stakeholders, the policymakers and industry leaders who are really driving emission mitigation efforts. Now, the remainder of my talk, I'd like to do a deep dive into some of the different applications of the IMI and how we can use it to quantify methane emissions across scales. So as we've seen already, one of the key applications of the IMI is to evaluate countries' official emission inventories, or the national emission reports to the UN Framework Convention on Climate Change, the UNFCCC. And this is an example of how this can look from a recent paper by Zichong Chen et al. In 2023. Zichong used TROPOMI observations to optimize methane emissions for 23 countries in the Middle East and North Africa at 25-kilometer resolution. In all cases, the prior estimate, or the best guess starting point for the inversion, was from the country's submission to the UNFCCC. The table here shows some example results in terms of the differences between the posterior optimized emission estimates and the prior best guess emission estimates, broken down into different industrial sectors and also the anthropogenic total. For example, if we look at Algeria, it would appear, based on satellite observations, that the national emission report from Algeria underestimates methane emissions from the country by about 75%. And the bulk of that underestimate is due to underestimates in methane emissions from gas production. By contrast, if we look at Iran, the anthropogenic total emissions reported to the UNFCCC are very similar between the inventory and our satellite assessment. But if we look at some of the industry-wise breakdowns, we see that there are some important discrepancies. So, for example, estimates of methane emissions from oil production in Iran seem to be dramatically overestimated, while estimates from gas production, livestock, and waste are significantly underestimated. We can repeat this exercise in other parts of the world, including South America, for example. These are results from a paper recently submitted by Sarah Hancock et al. In 2024 that used the IMI with TROPOMI and GOSAT data to estimate methane emissions from individual countries in South America. Now, Sarah found that South American anthropogenic methane emissions are about 55% higher than reported to the UNFCCC. The emissions are dominated by livestock, about 65% of the total. The satellite estimates actually match reports quite well for Brazil and Bolivia and Paraguay, but are much higher than reported elsewhere on the continent. And Sarah finds that this is likely because official cattle emission factors, the estimate of the typical emissions of methane per cow, are about 50% too low everywhere except for in Brazil and Bolivia. So these are examples of how we can use satellites to find areas of potential improvement in countries' national emission estimates and ways to improve these official emission inventories. We can also apply this framework to evaluate the EPA inventory for methane emissions in the United States at 25-kilometer resolution. This is work from Hannah Nesser et al. In 2024 that used TROPOMI observations to correct the 2023 US EPA inventory. The correction factors are shown here on the left. These are the correction factors needed to bring the EPA inventory more into line with observations from TROPOMI. Overall, Hannah finds that the emissions in the EPA inventory are too low by about 13%, and if she breaks them into the component industrial sectors, she actually finds, in some cases, larger discrepancies. So in this plot here on the right, the shaded bars are posterior emission estimates. The unshaded bars are prior emission estimates. Hannah's finding that according to TROPOMI observations, the EPA inventory should report about 11% more livestock emissions, about 12% more oil and gas, about 30% less emissions from coal. In other words, Hannah's finding that the US EPA inventory is overestimating methane emissions from coal, but also that it's significantly underestimating methane emissions from landfills by a factor of about 50%. And so Hannah looked into this and found that this is likely because the EPA emissions for individual landfills have large errors. Those could be due to overestimates in gas recovery, overestimates of the decay rate of methane emissions from the landfill, and then also from inadequate accounting of operating practices between landfills, which can vary significantly from site to site. Now, this is an example of this new 12-kilometer capability that we're introducing into the IMI. This is work from Xiaoling Wang et al. In our group from 2024, still in prep. And Xiaolin has applied the IMI, looking at TROPOMI observations, to estimate methane emissions from large U.S. urban areas. And here's an example of what TROPOMI sees around the Atlanta urban area. And we can see that within the metropolitan boundaries, there are some high methane concentrations in the dark red colors there. Overall, what Xiaolin finds is that the EPA inventory generally is underestimating methane emissions from cities. For 7 of these urban areas, the underestimates range from about 12 to 400%, and that major outlier is for Miami. So we have some very large underestimates in some cases. By contrast, emissions for Los Angeles seem to be overestimated by about 30%, 36% in the EPA inventory, and these other cities are relatively well captured. Zooming in a little bit to the LA area, Shaolin finds that some of the hotspots in our satellite-based emission estimates, especially at this 12-kilometer resolution, correspond closely with the locations of active landfills, which are shown here as magenta circles. And this is something that's not so clear in the default 25-kilometer resolution product. So it really shows the power of increasing the spatial resolution of these inversions. Now I'll switch gears a little bit and talk about a different application of the IMI, which is for continuous monitoring of emissions from regions of interest. One of the great strengths of TROPOMI is that it has daily observations of the whole world. So we have really high frequency information coming in about methane every day. And we therefore have an opportunity to use this to continuously monitor emissions over time. As more data come in, we can update our estimates. And so this is what we've done in IMI 2.0. We have introduced an option for this application. Example of it in action is shown here for the Permian Basin again. In the top left here, I'm showing 1 week of a typical week of TROPOMI observations for the Permian Basin, where again we can see these hotspots over the centers of production, the Delaware and Midland subbasins. And then in the bottom right, the results of 127 consecutive weekly inversions using the IMI. So those are the black points showing our best estimates of the total methane emission rate from the basin every week. The red line is showing a 4-week moving average. And so in this study, what we found is that methane emissions from the Permian are extremely variable, especially on multi-week scales. And as part of the study, we tried to investigate what might be driving those emissions. We found that 2 of the most important drivers appear to be new well development, the rate at which new wells come online to produce oil and gas. We found that on a couple of occasions, large increases in the rate of well development led to surges in methane emissions, and then also trends in natural gas prices. In particular, we saw a period when the local natural gas price crashed dramatically, and during that period we saw a strong uptick in methane emissions. So we can extend this work to look also at trends in methane intensity from oil and gas basins. So methane intensity is a measure of the efficiency of oil and gas operations. It's defined as the amount of methane emitted from an oil and gas basin divided by the methane gas produced. So for example, here for the Permian Basin, during this period from May 2018 through nearly the end of 2020, we see a mean methane intensity of 4.5% for the Permian. That means that of all of the natural gas produced and sent to market in the Permian Basin, 4.6% of that was also released to the atmosphere. Now, interestingly, we see a decreasing trend in the methane intensity during this period by about 1% per year, from 5 to 6% in 2018 to 3 to 4% in 2020. And this would indicate some improvements in operator practices, because during this period, oil and gas production were surging. However, these methane intensity levels are still an order of magnitude higher than the industry targets from the Oil and Gas Climate Initiative, or OGCI, which is to get below 0.2% by 2025. So there's a lot of work still to do. Now, we obviously want to be able to monitor this operationally and continuously. And our vision for an operational continuous monitoring system with the IMI looks something like this. We start with a triggering event, which can be very simple, something like, it's Monday morning, we want to run some inversions before people come into the office for our regions of interest. This leads to the IMI being deployed to an AWS compute instance through a software container. The inversion is automatically run and the results pushed to the simple storage service, or S3, that's the main storage service in AWS. And that's where the results reside for the user to then go and inspect them, but also to be used as the prior estimate or the starting point for the inversion in the next update period. And this is an example of what this framework might look like in action for 5 U.S. oil and gas basins: the Permian, Anadarko, Barnett, Eagle Ford, and Haynesville. Those are in Texas, New Mexico, Oklahoma, and Louisiana. And the plot here on the left is showing weekly methane emission estimates from the IMI for these 5 basins for the years 2022 and 2023. We generated this plot about 3 weeks into January of this year. And so that's our real latency right now, is maybe 3 to 4 weeks. We're working on getting that down to just a couple of days so that we can run this framework closer to real time and, say every Monday have information on what happened the previous week. But already from here, we can see some interesting trends. One is that in the Permian during this period, there appears to be a seasonal trend with higher emissions during the winter and lower during the summer. And some other research groups have seen this as well, but the reason why is still under debate. More generally, all of these basins are showing over this 2-year period relatively uniform or even in some cases decreasing emissions despite surging production everywhere except for in the Barnett Basin. And so that would indicate that as recently as December of 2023, that trend we saw of decreasing methane intensity is continuing for U.S. oil and gas production. And the last application that I want to show today is applying this continuous monitoring framework to Turkmenistan. Turkmenistan is a country in Central Asia that's a major producer of oil and especially natural gas, and that has had the methane spotlight on it now for several years, going back to the discovery in 2019 by GHGSat of extremely large methane point sources from oil and gas infrastructure in the country. And the plot in the background here is showing detections of methane superemitters, or very, very large point sources, seen by TROPOMI and documented by the Varon, Netherlands Institute for Space Research. This is just for the year 2023. So we have very large methane emissions coming from Turkmenistan, from oil and gas, and there have been ongoing diplomatic efforts to try to understand why and what might be done about it, including most recently taken up by the Biden administration. And so our contribution to all of these efforts and the scientific studies underway is to monitor methane emissions across Turkmenistan every week and observe trends over time. And so these are some preliminary results from that work. On the top left here, I'm showing the weekly methane emission estimates, the national totals for Turkmenistan over 4 years, from 2020 through the end of 2023. The average emissions during that period are about 6 teragrams per year. It seems like there are 2 regimes of variability, where in the first half of the time period, there's a sort of uniform march upwards, and then starting about August 2021, what looks like a seasonal variability sets in, this time with lower emissions in the winter than in the summer, which is opposite what we saw in the Permian Basin. The graphic to the right here is showing the same results, but as a map of weekly emissions. It shows the emissions moving around the country over time. And something we like to do to validate and provide confidence in our inversion results is to compare with independent observations. In the US, we often have a wealth of independent observations. There may be ground observations within an oil and gas basin, say from a tall tower network, or from aircraft who have flown around the basins or around a city to study methane emissions. But in Turkmenistan, we don't have that. However, what we do have are independent detections of point sources from many of those satellites that I showed earlier in the talk when we were looking at the methane observing system. And so what I'm showing here is a scatter plot of the sum of point sources detected every week during 2023 by all of those different instruments compared to the regional total emission estimates we get from the IMI and TROPOMI during that week. And we see here that we have an excellent correlation, an R value of about 0.85. And so this is one way that we can really lend confidence in our inversion results. And so I'm going to end my talk there. I hope I've given a useful overview of the methane problem, why we need tools like the IMI, how the IMI works, and some of the applications that we can use it for to help support methane emission mitigation. Again, I'll say that the IMI is an openly accessible tool on the AWS Marketplace. All you need to access it is an AWS account. If you're interested in trying it, I would encourage you to check out the IMI website and also to contact our development team. Again, I'm Daniel Varon here, the second name from the bottom. Feel free to reach out to us with any questions. We're very responsive. We like to help people get set up with the tool. And also, we are planning a virtual user workshop for the IMI later this year in October. If you're interested in attending that, feel free to reach out and we will keep you in the loop. So with that, thank you very much.